Welcome back to the channel. This is Nate Webb. Hey, so today I am talking about a number of different things when it comes to wiring again. Using LED lighting, wiring. I'm not really going to get into like how to wire on this one, but I'm going to get into what types of wire to use and why. And we'll touch a little bit too on this kind of fairly quick video in regards to corrosion and how to prevent it. And there's a number of different ways, and I'll talk about that in a little bit more depth on a deeper video. I'll even try to dig up some more of our corrosion types of preventative materials that we use. But I've got something on the bench today. I was looking around the shop trying to find things to talk about with corrosion because corrosion is one of the things I think we deal with the most in our industry. We see places where things rust and corrode away, deteriorate, various things like that. And there's two levels of it. So one of the things, like living in Colorado, we enjoy the fact that most things don't rust out, right? So our vehicles don't rust away. I've got a 1977 Chevy van sitting in my lot that is needing some restoration, and there's a lot of raw metal and things like that. And a protection coating of rust will get on it, so it's just that light kind of rusty color. And I'm not worried about that metal rusting away because I'm not getting it wet all the time. So even when it snows and rains, I'll wash it off after each spring or in the spring or in the fall or something just to get all the dirt and muck off of it so that it doesn't continue to rust. But I'm not worried about it getting wet because the wet really isn't the part that makes it rust. Where rusting really gets crazy, and really what I'm talking about is corrosion, is when there are electrolytes. So when there's dirt and other types of electrolyte types of materials, this could be phosphors, it can be, any kind of mineral that's in the water or in the air that it bonds with the rain. And then if water just continues to drip across a piece of metal, it will get rusty. That will be the first level of it. Any kind of metal, I mean, even aluminum. The reason that we anodize pieces of aluminum like this is to keep that black dust from forming on aluminum. Well, that black dust is aluminum rust. People say that aluminum doesn't rust, but unless it's anodized, which is a protective coating that's electroplatedly or electroplated onto this. I might not be saying that right, but it's electrolytically plated. I'm not saying that right. Aluminum will still rust. Now, does it rust away and turn into things where it falls apart? No, because that protection layer that aluminum does typically blocks any additional rust. I have a trailer that's got an aluminum roof. And where all the electrolyte water has been running over the sides of it for years, there are these black trails. Well, those black trails will eventually rust. And okay, so I have a trailer, a semi trailer out in my yard, and it's made out of steel and aluminum both. And this is a door latch off of one of the doors. So this is actually one of the top doors. So if you can imagine all the rain coming off the top of the trailer and rolling around, and this actually ate out the weld behind this latch on the top of one of the doors. So one of the days I went out there and closed the trailer up, and this latch got stuck in the top, and thankfully it didn't fall on my head. But when it did land, it was pretty interesting because it didn't rust out the latch per se itself. It rusted out through probably a pinhole or a micro pinhole in the welding that attached this piece to the trailer. So that whole entire top beam across the back of that semi trailer is shot. I mean, it's like rusted completely away. And that really shows the difference between steel that lives in a really heavy wet environment like upper Minnesota versus Colorado. So in Colorado, like I was saying about the van and most vehicles, old vehicles, they just don't rust away. Out here in the western states, you'll be driving along on interstates or back roads and highways, and you'll see old cars sitting out in fields, and they're not rusting away. They've just got that nice protected coating of rust on them that keeps them. And a lot of times that'll displace the paint and that'll do a lot of those kinds of things. But for the most part, the steel is structurally still there. Where the steel gets worn away the most is through corrosion with wet constantly, or pooling water, or water that just sets in there, all summer long. That would rust out the steel, even here in the West. But a lot of times it's so dry that even those puddles, they dry up and disappear, and it doesn't rust. Where rust is actually in an LED lighting system, we enter into a whole completely different type of corrosion. Corrosion in electrical and lighting systems is called galvanic corrosion. And the reason what we're doing there, the reason they call it that is because it's actually an accelerated type of corrosion. It's where two pieces of dissimilar metals match up to each other. In my training, I get really in depth on how to match up metals. So, different types of aluminums versus stainless steels and other types of galvanized steels to make sure that you match up these things properly so that they don't react to each other. There's high galvanic types of materials and low galvanic types of materials, high densities and other types of things. And I'm not always saying that right on this video. I usually sit down with a lot of my notes and get detailed on that. But basically, the densities of metals like aluminum and steel, they're not going to react to each other. But galvanized metals and steel can react to each other, or galvanized and aluminum, or galvanized and even stainless can react to each other. And this is where you see things like street signs. So they'll have a street sign mounted. It's a galvanized pole, post, or something. It goes down to like a nickel or zinc plated bolt or some type of attachment into the concrete. And because those two metals don't react to each other very well, they have galvanic corrosion when that water gets on it. Those two dissimilar metals reacting to each other, and one is going to die. One's going to lose out. Another place you'll see galvanic corrosion a lot is in like dams and underwater metal things, boats, steel ships, things like that. And they'll have a sacrificial plate, some type of anode or cathode that will be put onto whatever steel is there. And that is where most of that galvanic corrosion will happen. And those plates need to be replaced. Sometimes as little as like every month or every couple of months, they'll go down and replace those plates to make sure that the main primary steel does not rust away. So giving a sacrificial plate for the galvanic corrosion to happen. In the electrical systems, we see this in automotive. A big problem that happened in automotive is, what you typically see. I would say the biggest place you're always going to see corrosion when you open up your hood is going to be right on the battery terminals inside your engine bay. Every time the battery is there, those two dissimilar metals, the leads or whatever the terminals are made out of, the softer metals, and then the attachment, grip points or wire connections, and then the wire itself is copper. And sometimes it's aluminum. And so all of those kinds of things don't react well to each other. And then you add the low voltage. You add the 12 volts to it. You add the high amperage 12 volts to it. And that's where that corrosion can accelerate. So in automotive, we want to put that little red goo on there to kind of keep that corrosion mitigated. It kind of protects it, creates a layer of protection. But still under the surface, corrosion is still happening, right? It's just ideally the moisture that gets in there, that third part of, I would say, the corrosion triangle is not getting in there, right? So the third part is the moisture. And if you can displace the moisture, most of the time you're going to eliminate the corrosion or just keep it to a surface level. In electrical systems, and I've seen this in junction boxes, I see it everywhere. You can't keep water out. You can't. I don't care what anybody says. You're not going to put enough electrical tape on it. You're not going to put enough heat shrink on it. You're not going to put enough corrosion X or dielectrics or any of those kinds of things to keep corrosion from getting into it. So what you want to do is you want to minimize the corrosion as much as possible. Here's a couple of things I've found. This just comes from working on it. I used to use WD-40, and I think actually WD-40 is a pretty good one, but you just have to apply it a lot. WD-40 in and of its name, water displacement formula number 40. I mean, that's really what it comes from. But there's been some really great advancements in techniques and technologies since then. A number of years ago, there was a yellow or an orange can out of Canada. I can't remember what it was called. I don't remember, but it was a good corrosion protection. It was better than WD-40, and we would actually spray it on all kinds of things, and it would last. It stayed on the surface of most things for a while. In our Christmas light program, it would displace the corrosion and protect that. What I'm using now is this product called Corrosion X. And this is not a product, they're not sponsoring me. I wish they would. Hey guys, Corrosion X, you want to sponsor me? I'm all for it. But Corrosion X, I'll tell you what, this is one of the best things out there, and here's why. It says it kills corrosion, kills rust and corrosion, safe on electronics or electrics. World's greatest lubricant, penetrant, and anti-seize. Dude, I'm telling you, this stuff is great for everything. I use the red can. If you go to their website, they've got a dozen different things. A lot of the formulations were made for aerospace and aeronautical engineering applications were life safety, right? You don't want an electronic system in an airplane to corrode out and all of a sudden it doesn't work. The battery all of a sudden corrodes and doesn't work. So Corrosion X. In fact, I actually use this on all my automotive programs, projects. I put it in all of my wire connectors when I'm working on cars, and I use it on just about every electronics thing that I use. They make it in these little spray cans, but they also make it in big giant jugs, 5-gallon buckets, pump spray cans, all kinds of stuff. I think they even make it in like you can get a 55-gallon drum of it if you want. But in that corrosion, what begins to happen are things like the wires begin to eat up. So the same kind of super mega deterioration that happens here, imagine it happening on an Edison connector inside of a receptacle in a junction box in a landscape. Imagine it happening on, micro little connection types like this. Inside of this connector right here is just really cheap metal, pot metal, right? So the connections, and when those connectors come together, they're making a connection, albeit low voltage. They're still low voltage here. In this particular application, there would be 12 volts. That's actually not a very low volt, frankly, when you think about it. And then there would be a data signal on this thing. This here is a tiny little digital lighting controller. I mean, these are pretty great. They'll do about 160, maybe even 200 different lighting effects on digital lights. But 12 volts, and those little tiny connectors, they rust away, they corrode away. So one of the parts about galvanic corrosion is dissimilar metals, water, water with electrolytes in it, and then you add in the electrical. The electrical is what really begins to start, I would say, just accelerating and causing more damage at an accelerated rate. So if the electrical wasn't there, it might rust over a period of years. Whereas if the electrical signal or the electrical voltage is there, it will accelerate that corrosion at lightning speeds. I've got a pretty crazy story, as I kind of unbolt this guy. I'm going to take this apart right here. As we start to take this apart, I will tell you guys this story. Oh, sure, I don't have a screwdriver on the bench. Let me grab a screwdriver. Okay. Not the greatest screwdriver, but a screwdriver nonetheless. Okay, so as I take this thing apart, I'm going to show you some stuff on the inside of here. This is a power supply enclosure, so I'm going to take it apart, and we'll talk about it. So here's the story. Working on a historical building, putting together a lighting system, and all of a sudden we got budget to go ahead and improve the lights, right? Let's put some new lights on. So brand new technology, new power supplies, and these great fixtures. Fixtures were amazing. Everything was awesome. Super happy about it. The historical lighting system. I mean, this lighting electrical rig was probably last done in that area. Oh my gosh, it's probably the 1970s. So they actually had electrical in the building that didn't have proper grounding. Didn't really think much about that, but proper grounding is actually really important, especially with ground fault interrupters and other kinds of things. Well, on this historical building owned by a city, it didn't matter much, right? So they didn't care as much about that at the time. So they were doing what's called shared grounding. So 2 or 3 or 4 circuits would share a ground. And in this particular case, I think there was maybe 12 or 14 circuits going to this one area that were all shared on a bonding ground, which also was the lightning rod. You gotta love it. But the lightning rod was this big copper wire. It was probably like a number 4 or something copper wire from the top of this tower area or this lightning system down. And everywhere the electrical would cross like a sub panel or even some outlets, you'd see this little ground wire come out and grab on with a little ground bus, and it was like, that's interesting. So what ended up happening on this project, we installed the new lights, and about 2.5, maybe even 3 years later, all of a sudden you would go up there and touch the chassis. Like you would just touch the metal and you would get a little bit of a voltage buzz. And, I couldn't feel it on my fingertips. I didn't get it on my fingertips, but I got it right here on my forearm. So I'd touch my forearm to it and it was like, ooh, yeah, there's a buzz there. So I break out the voltmeter. Maybe I break out the old fashioned voltmeter, right? So this old Radio Shack voltmeter. And I start checking volts, and I'm getting 65 volts between ground and neutral. Or I'm getting 65 volts between the chassis, a little screw point, and the ground itself. Whoa, what's going on? Something's happening. This is crazy. Why am I getting 60 volts? So long story short, what ended up happening and what we ended up finding out over time, the new power supplies have what's called a shunt in them. So these new big power supplies that I had here, I'll show you, this big guy right here has probably got them in there. There are called safety shunts inside of these big power supplies. So a safety shunt is essentially a way to protect people from getting electrocuted. Great idea, great concept, obviously new code. This is what the future of electrical is doing. They're putting in these safety shunts into these systems. Now, a safety shunt in and of itself is the theory says, hey, keep voltage from happening, right? And ground is always supposed to be there so that you have a place where that transient voltage, that 65 volts I got on my forearm, needs to go somewhere, right? So if the ground is properly working, it just drains away on that ground, no problem. When you're adding that 60 volts or that shunted voltage into the grounding system, really interesting properties there. And I'm gonna do a white paper on this whole thing and a study, and maybe it'll accompany with a bigger, longer kind of thesis video on this whole system, because this was something that was crazy. But what ended up happening in that is that this one ground system, there was one wire that was feeding these 8 or 10 circuits and the lightning rod. Between those two grounds, the voltage was backhauling onto this one ground back to the main panel. And over time, water had built up into two pieces of conduit. So imagine it's an old building. So you've got steel pipe meeting into that's like inside the stone and concrete. Then it comes down and it meets up to an EMT, which is an electro galvanized metal tube, right? So those EMTs are all galvanized. Well, they mismatch each other. Because this pipe goes outside of the building, water comes into that pipe, gets inside of there, settles inside one area or part of that pipe. Where those two dissimilar metals meet up with a little bit of water, now add the electrical issues to it because we put new power supplies, which are shunting voltage from the line and the neutral and the ground, all to ground, through these shunts. There's now accelerated corrosion happening. So somewhere buried in the concrete, or somewhere that we couldn't have access to a wire and the conduit pipe. I believe they were actually even using the conduit pipe as the ground, which is some of the old ways to do it too. I think that's in my notes. Those pipes were the ground. So when they had water in them, the corrosion accelerated until they just fell apart and they just basically disconnected from each other. Not a problem, except for now that shunted power doesn't have anywhere to go. So it was just going into the ground wire and electrifying chassis. So anytime you see that, so like in here, if you look real close, you can see the ground wire is actually bonded to the chassis. So down here in the bottom, you'll see that ground wire bonded to the chassis. So that is proper electrical situation. That's how you always want to do it, is bond that. So if for whatever reason that becomes electrified and I touch it, it should drain that voltage away, causing either a breaker to trip or GFCI to trip or something like that, right? So you want that to happen. And in this particular case, that ground was the conduit pipe. It corroded completely away. The ground went away. The shunt in the brand new kind of modern electrical safety shunts in that power supply shorted that voltage right straight to the chassis, electrifying the chassis. So most of them we had between 60, 75 volts. Others we had as much as 300 volts. And some of the actual places where we were doing various things, there was some electrocution issues and a bunch of other stuff that ended up happening. Guys got electrocuted, shocked. I wouldn't say electrocuted because that would be like, they died from it, but they didn't. But it hurt. It hurt, and it scared you because it was something you weren't expecting, because you kind of expected all the electrical systems are meeting code and should be proper. So we ended up going into that project and having to sort out the issue. And because it was a little bit above our pay grade and what we were doing on that project, we needed to have another contractor come in and pull some new ground wires. Once we pulled the new ground wires, put it all back together, fired it right up, everything was super, super safe, never had a problem again after that. In fact, I think even for that one season, we ran a temporary ground through some extension cords and some other stuff to bring that all together. Didn't have any problems, but that's where galvanic corrosion ultimately ended up causing us to get shocked. Not life or death safety shocks, but, it could be, because it doesn't take a whole lot. That's why these GFCI trips, 0.5 millivolts, which is hardly anything. It's hardly anything for power, because people do die of electrical shocks. So that's something to be considered, and galvanic corrosion led to that thing being a problem. So wherever we can, you use Corrosion X or some type of anti-corrosion type of material, Corrosion X. Hey, if you guys are watching, sponsor me. I believe in this. I will wear your shirts for sure. And then where it really gets down and dirty to it is modern power supplies, safety shunts, electro galvanic corrosion is where we have problems. If you guys like this video, you want to hear more about this, you want to do one of my training courses, we get really deep down into the metallurgy of how metals dissimilar metals don't like each other, examples of galvanic corrosion, see how galvanic corrosion can be accelerated, and even see some time-lapse videos and other things that we're creating right at the moment. That would be great. I would say like and subscribe, reach out, give me a contact, give me a shout, let me know if you guys want me to come out and help you guys learn about galvanic corrosion and why that works and why it's important. And we'll talk about that more in the future. Thanks for joining me on this video. Like and subscribe. See you guys on the next one.